we shall start our discussion on magnetic field in material medium. Earlier we have investigated magnetostatics in vacuum. What does magnetostatics in vacuum do? In magnetostatics vacuum, we consider a conductor which carries a steady current, and we have found the field at a point P having position vector r, and it was assumed that there were nothing in the immediate neighborhood of the conductor except the conductor r. So this is the magnetic field in vacuum, and we calculated the field either by applying Biot-Savart law or applying Ampere circuital law. An alternative way of calculating the field was via the introduction of vector and scalar potential. However, we could find out the field at a point when there is an isolated conductor, and this field, now we call this field is the vacuum field, or the field due to the conduction current, so we call it I field. This is the due to the current flowing through the conductor. We have calculated these are the vacuum field. Due to conductors, and this problem has been well addressed in magnetostatics of vacuum that we have discussed till the last lecture. Now the problem is that we have a magnetic material placed in its neighborhood. Then this current carrying conductor produces a magnetic field. This magnetic field, in some way or other, produces some magnetic effect within the magnetic material, which in turn contributes something to the field at P. So the addition is the field due to the magnetization, or this is the magnetization field, field due to magnetized material. Our primary objective in this study is to find out Bm, so that the resultant field at the field point would be B is equal to Bi plus Bm. As we have already aware of the techniques for calculating this, we are only concerned with this and the additional field due to the magnetized material. And if you want to find out the total field, one has to add up the field due to the conduction currents. So this is our objective. We have investigated a similar situation in electrostatics too. So let me recall what we have done in electrostatics before going to the magnetic material. We found that if we have a charge or charge distribution, then it produces a field, and we call it the field due to the charges or conduction currents. This is the conduction charges, the field due to the conduction charges. And if we place a dielectric material in its neighborhood, then this field produces polarization. What is polarization? If the atoms, the dielectric atoms are such that the center of positive charge and the center of negative charge were coincident, then this dielectric atom would have no atom or molecule would have no dipole moment. But whenever a field is applied, if you apply a field in this direction, the positive charge, center of positive charge moves in the direction of the field, and the center of negative charge moves in opposition to the field, and this charge separation is produced. So as to say, an induced dipole is produced due to the charge separation. This is called deformation polarization. There are other types of dielectric material in which the center of positive charge and center of negative charge were already separated even in absence of external electric field. When an external electric field is applied, two things happens. One is that this separation between the center of charges undergo a change. This is this is the induction effect that is similar to this. And another prominent effect that takes place is the dipole, when placed an electric field in a uniform electric field, it experiences a torque P cross E, where P is the dipole moment and E is the magnetic field, electric field. So under the action of the torque, the dipole tries to orient themselves in the direction of the external applied field. Before the application of the field, the dipole, although there were non-zero dipole moments in a polar dielectric, due to thermal agitation, these dipoles were originated randomly, and so that the net dipole moment over a macroscopic volume was found to be zero. So whenever the electric field is applied due to the torque acting on the dipole tries to align themselves in the direction of the field, in the direction of the external field, so as to minimize the potential energy. With the potential energy, remember that the potential energy is this, and which is a minimum when the dipole moment is directed in the direction of E, in which case the magnitude is minus P times E. This is called the orientation polarization, and we generally define the polarization vector P, which is the induced dipole moment per unit volume, and under dipole approximation we found that the field due to this polarized material is found to be 1 by 4 pi epsilon 0 The geometry used for this is this. The same geometry that we are using repeatedly. This is a magnetized material contained within a volume V prime and bounded by a closed surface S prime. Our aim is to find out the field at an external point, remote external point, that is, the coordinate system is so chosen that this distance is small compared to this. In general, this phenomena happens in the atomic dimension, and we generally find out field at few centimeter away. So the R is much greater than R prime, so that it is sufficient to retain the first order term only, and this is the relative coordinate R, a relative position R. This is the geometry that we have used, and interestingly it was that this volume polarization charge density is given by at the point. These are the, and we argued that these are the field coordinates, we need not to equation, we need not to write primes when we are defining the rhos and sigmas, because the left hand side and right hand side refers to the same point. But whenever we use this equation within an integral, we must differentiate between the integration variables, so primes are used in general. So, so the conclusion is that if you know the polarization, you can define as volume and surface density of polarization charges, and you can calculate the electrostatic potential corresponding to the polarization charges, and from where we can go to calculation of the part EP, the contribution to the field due to the polarized material. So this is the resultant field would be EP, and this is equal to E. And if you take the gradient of it, the field becomes just as the, let me write afresh. This is the field due to the polarization, so the problem was solved in this way. In magnetostatics, we are going to adopt the same procedure. One thing you may note that whenever we are considering the induced polarization is in opposition to the applied electric field, and the orientation polarization is in the direction of the applied field. Now let us come to the magnetostatics. What happens in magnetostatics? If we consider a material, the material is ultimately composed of atoms, and in atoms we have electrons which revolves around the nucleus. This is the nucleus, and the electron revolves around the nucleus in a closed orbit. For hydrogen, hydrogenic electron in n is equal to 1. For hydrogen atom, n is equal to 1 state, the frequency is of the order of 10 to the power 15 Hertz. So, and n is equal to 1 electron of hydrogen atom makes almost 10 to the power 15 revolution in a second around the nucleus. So the electron appears to produce a continuous charge disk, appears to form a closed current carrying loop. We know from our study in magnetostatics that a closed current carrying loop, so far an external point is concerned, behaves as a magnetic dipole whose dipole moment is the circulating current times the area. So if we consider the electron to be revolving in a circular orbit of radius r, first thing is the current. Current is minus E times nu, and this is equal to minus E omega upon 2 pi. And the dipole moment is pi r square into r. This is current. This is dipole moment. This comes out to be minus E omega upon 2 pi into pi r square. So this is equal to E by 2 m r square, omega r square. Omega into r is the velocity, linear velocity. So this is m, this is the linear momentum, times r is the angular momentum, so we write it as minus el by 2m, where L is equal to mvr is equal to angular momentum of the electron in the circular orbit. So it is found that the dipole moment of the electron revolving orbiting around the nucleus is related to the orbital angular momentum. This is the classical relation valid for electron moving in circular orbit. In quantum theory, it is found that this simple classical idea does not hold. Rather, the angular momentum associated with the orbital motion is quantized, and it is given by Eh cross by twice me. This is PL, is the angular momentum vector, which we have written as L. This is PL. This is times, this is the quantum number associated with the orbital angular momentum number. As for Bohr's theory, we know that if we have angular momentum PL, then the values of PL is L into H cross. So this PL has been replaced by LH cross, H is there, and this quantity is known as Bohr magneton. Electron Bohr magneton, and the orbital angular momentum is found to be quantized in units of Bohr magneton. However, the spirit is that whenever electron moves around the nucleus, it produces a closed current carrying loop, so the electron orbital motion can be associated with the orbital dipole moment and the orbital dipole moment. So these tiny dipoles, these are the dipoles of atomic dimension, because this radius is of the order of Bohr radius or something more. These tiny dipoles these tiny dipoles are oriented in different direction. If we have an assembly of atom or a single atom comprising of a large number of electrons, then each electron produces such a dipole, and these dipoles are oriented in different directions. And so, in general, the dipoles are oriented randomly. So if we consider a macroscopic volume, then within the macroscopic volume dV, there will be of the order of 10 to the power 6 or so number of atoms, and each atom there will be more than one electron. So all these tiny dipoles will be oriented at randomly. So if we average or if we take the vector sum of the dipole moments of all the atoms within the volume dV, it generally comes out to be 0. When a magnetic field is produced, firstly what happens that the orbits of electron orbits gets deformed. In the case of deformation polarization, the electric field, the external electric field changes the direction between the center of positive and negative charges, thereby producing an induced dipole. Here, the electron revolving in an orbit when placed in an magnetic field experiences Lorentz force, and due to this action of the force, the electrons orbit gets deformed. The situation is complicated and the deformation is in a complicated way. However, it is found that under the action of the force, the electron will trace a trajectory which is different from one which it was following in absence of the field. So the electron orbit will be deformed and thereby giving rise to some additional dipole moment. This additional dipole moment is due to the induction, and as a general property of induced effect, it tries to oppose the external field that has caused this deformation. That is to say, due to this deformation effect, the magnetic field that is produced is in opposition to the applied magnetic field, and this is called the diamagnetism. This phenomena is called the diamagnetism. Copper, zinc, aluminum, lead, mercury, they are the examples of diamagnetic materials. Another phenomenon that occurs is the orientation problem. This dipole, say we are applying a magnetic field in this direction, and a dipole was originally, this was the electron orbit. Due to the deformation, this orbit gets deformed. We are not, at present we are not considering this, we are considering another effect. This is the normal to the dipole direction. This dipole experiences a torque. This is given by m cross b, and the corresponding potential energy is minus m dot b. Here we assume the field to be uniform. So under the action of this torque, the dipole will try to align themselves in the direction of the field, and so as to make the potential energy a minimum one. But this effect will be opposed by the thermal agitation. Due to the thermal agitation, these dipoles were distributed randomly in all possible directions, and whenever an effort is being given to orient this dipole, there will be a tendency of the dipole to orient themselves in the direction of the field, but there will be a competition between this orienting tendency and the opposition that is offered by the thermal agency. In the absence of the thermal energy, a slight amount, a very small amount of magnetic field would cause all the dipole to orient in the direction of the field. But due to the thermal motion, a larger amount of field is needed to orient all the dipoles in this direction. So if we consider the orientation in this direction, and this is the field at a particular temperature, this the curve will be this. This is orientation, a measure of orientation. Actually, this will be the magnetization that I will come later. It is seen that when zero field is there, no orientation, the dipoles were distributed at random. Whenever the field increases, we set the field then the dipole will try to orient themselves in the direction of the field, and the orientation will increase with the increasing magnitude of the field, and at a particular instant it will found all the dipoles get oriented in the direction of the field, and this is called the saturation orientation. If we increase the magnetic field further, there are no more dipoles to get oriented in the direction of the field. This is the saturation magnetic field. This depends on the temperature. The larger the temperature, larger is the B field required for the saturation. So the phenomena is very similar. The dipoles which the dipole moment that arises due to the polarization effect, due to the orientation effect, gives rise to a field which is in the direction of the external field, and this phenomena is called paramagnetism. Now we come to define the quantity analogous to P used in the case of electrostatics. In electrostatics, we consider a macroscopic volume delta V. By macroscopic volume, we mean that delta V does not go to zero, but macroscopic volume delta V, which contains approximately 10 to the power 6 atoms or so. It is found that delta V does not tend to zero, but the delta V by V, this ratio tends to zero. This is the definition of macroscopic volume element. We consider the atoms within this volume. Then each electron within the volume has a dipole moment mi, the dipole moment of the ith electron, and we then what we do, we calculate delta m is equal to summation over I of mi. This sum is over all the electrons within delta V. So this is the vector sum of all dipole moments of all the electrons within the volume delta V. Then we carry out the ratio. And we found that this ratio with decreasing delta V tends to a limit, and this is called the magnetization, so to say, induced dipole moment. Magnetization vector, it is equal to induced magnetic dipole moment, per unit volume. This is the magnetization. This is the quantity analogous to polarization P we introduced in electrostatics. Now, if we have n number of atoms within the there are n atoms, n electrons within this. If there are n electrons per unit volume, and then magnetization is defined as n times m average, m vector average. So this is the average dipole moment per electron, and if we have n such electrons in unit volume, then this is the simple formula for magnetization. This, so far we have considered only the orbital motion of electrons, but experiment indicates that apart from orbital angular momentum, electrons do possess another angular momentum called the spin angular momentum. It is an intrinsic property of the electron, and correspondingly there will be a dipole moment arising from the spin part. In magnetic phenomena, this spin dipole moment is found to play an important role. The phenomena of ferromagnetic materials, antiferromagnetic materials, and these are entirely governed by spin phenomena. However, here we shall confine our discussion to the orbital dipole moments, and we assume that we know the magnetization somehow, and we shall try to develop the theory so that one can calculate the magnetic field corresponding to the magnetic field due to the magnetized material.